Okay, gas laws, chapter 18. Usually, when I do this chapter, I do it as one big chapter, but for the last couple of years that I've been teaching honors again with the AP classes, um, if you really want to get into it, it really should be broken down into two separate tests. So, do a little test on chapter 18, that's the May 11th test, and then the test after that would be chapter 19. The difference between the two chapters, the relationships really aren't all that different. The only difference is that the calculations you're doing in chapter 18 only refer to physical mixtures. So when you have gases together, the particles are hitting each other, bouncing off, but there's no chemical reaction, no bonds are breaking. And in chapter 19, take a look at how chemical reactions affect the gas phase and the calculations that you have to do. And the thing I like about the fourth market period, normally, this of course is not a normal year for us, but normally the nice thing about the fourth market period, it kind of ties everything together and it provides a good review for the final exam. Now, there's no final exam this year, of course, but the nice thing about chapter 19 is that you have to go back and you have to review stoichiometry. So all of those limited reagent, percent yield, percent composition problems, they come back again, except for now you're dealing with the gas laws. All right, so chapter 18, just physical mixtures. We'll get right into it. They start off by reminding you that when you change temperature for substances, all substances, when you add temperature or add heat, expand, at least until you add so much heat that there's a phase change. And when you remove heat, they contract. Or again, you contract so much that you change phase. You go from a gas to a liquid or liquid to a solid. Pardon me. Now, those expansions and contractions for solids and liquids, unless they change phase, are very negligible. So we don't approach calculations involving solids and liquids the same way we do with gases, because a slight change in temperature is a big difference in the sort of space that the material takes up or its pressure. So again, the book just reminds you that liquids and solids, the particles are touching each other, and so therefore expansion and contraction is fairly negligible. In fact, they would say that the contraction of solids and liquids are almost zero. But for gases, their expansion, they fill up whatever container you put them in, and adding heat, if you're going to maintain a constant pressure, for instance, requires a much larger container. So, you'll notice, for instance, tires on cars and bicycles. The pressure of those tires will change dramatically if the weather changes. Now, this next part is actually chapter 19. So I'm just going to write that to kind of remind you that this is a chapter 19 topic. But I'm going to throw it into the chapter 18 stuff because it's important to understand for chapter 18. They start talking about what they call the ideal gas laws. And the term ideal means that we are going to treat the gases a particular way that may not necessarily be 100% true. We're going to neglect some things so that we can make our calculations a lot simpler. And for instance, with gas particles, they are so spread out. Do they have Coulombic attraction between particles? Well, yeah, of course. One gas particle has a positive nucleus, the other gas molecule has negative electrons, and those positives and negatives attract each other. However, we said in scale, if the oxygen particles at room temperature were 6 feet tall, the next nearest particle on average would be 6 miles away. So, yeah, there is attraction between them, but that attraction is very, very small in terms of force. And it's so small that we can neglect it and still get very good calculations. So what they're saying when something is a point mass, what they're saying is that the mass of the molecule for the gases is very important. However, things like the size of the particles we can neglect. The Coulombic attraction between particles we can neglect. And again, it's a pretty simple explanation as to why we can neglect it. All right, so we got our little 6 foot tall oxygen particle right here, right? And we said that, all right, if oxygen is 6 feet tall, then the mean free path, the next nearest particle on average, is going to be 6 miles away. And so we put our other little oxygen particle over here, 6 miles away. And the reason why we don't care about the size of the particle is, let's say just for the sake of argument, we decide to double the size of this oxygen particle. Well, now a 6-foot oxygen particle, and it's going to have a circumference, right? We think of these as round spheres, so it has a circumference. And let's say that the radius of this circumference is, I don't know, let's make something up. Let's say 2 feet. Well, then that means that this particle over here also has a radius of 2 feet, and the actual distance between the particles is going to be 6 miles minus 4 feet. Both of the radii for the particles. So for 6 miles, we're looking at 5,260 feet per mile. So you're looking at approximately 31,000 feet. And the distance between them is going to be minus 4 feet, so 30,996 feet. That's essentially the same as 31,000 feet. I mean, if we go to 2 sig figs, they're the exact same number. So we decide we're going to double this particle and make a huge particle out of it. Let's say instead of, now 6 feet, let's make this guy 12 feet. All right, so now we got our 12-foot particle, and instead of having a radius of 2 feet, he now has a radius of 4 feet, which means that the particle on the other end also has a radius of 4 feet. So even though we've doubled the size of the particle, there's still 6 miles minus 2 radii, so 8 feet. You're still looking at 30,992 feet, which again is essentially 31,000 feet. So if we double it again and we make the particle 24 feet tall, this is a huge oxygen particle, 4 times normal oxygen, 4 times the size of the normal oxygen particle. Now we're looking at a 8-foot radius, and we're still 6 miles minus 16 feet. Still 30,984 feet away. Again, essentially still 31,000 feet. Now, you keep making these molecules larger and larger. Eventually, they're not going to have enough thermal energy, enough kinetic energy to stay in straight line paths, and they're going to start to clump together. But essentially, going from 6 feet to 24 feet, from a size 1 to a size 4, quadrupling the size of the molecule, it really makes no difference. They are all essentially the same in terms of the distance between each other, so therefore the identity of the particle doesn't matter. Now the mass does, but the identity doesn't. So when we neglect the identity of the particle and we neglect things like the attractions between the particle, when I say the identity of the particle, I mean the size of the particle, we call this ideal behavior. Now, I hate that they call it ideal gas law. There's no such thing as an ideal gas. All gases are real. The term ideal is a mathematical construct. We're simplifying reality. We are neglecting Coulombic attraction. We are neglecting particle size in space. That difference, again, between 31,000 feet and 30,996 feet, we're neglecting that. We're not taking all things into account, but we're still getting really good predictive results. That's called ideal behavior. Now, it exists not only for gases, but when you study biology, there's things like osmosis and other colligative type of properties. Colligative means where it depends upon the number of particles and not the identity of the particles. Those things tend to behave ideally also. So we'll learn about the ideal gas law constant coming up, I think, in video 3 of this, 2 or 3. But you'll see that gas law constant pop up in biology when it's even liquid and solid material, because really what we should be thinking of, instead of ideal gases, we should be thinking ideal behavior. Ideal behavior meaning we're not going to consider the attractions between particles, and we're going to neglect the actual sizes of the particles. All right, so how does a real gas differ from an ideal gas? In other words, the real behavior of gases versus the construct that we make for doing calculations. Good question, and normally it would be a good essay question, but I'm going to have to come up with some clever multiple choice questions for it. So you should take this down and put it into your notes, and I'll go over, it's actually 2 pages here. First part would be give the properties of a real gas and compare them to the properties of an ideal gas. And again, I wrote ideal behavior rather than ideal gas because I don't want you to think of ideal as only pertaining to gases. It can pertain to other phases as well. All right. Real gases have sizes. Certainly a helium molecule is going to be much smaller than a carbon dioxide molecule. And the particles do attract each other. Even though they are far away from each other, they do impart Coulombic attraction. And therefore, when we talk about in the video I did on chapter 15, where we were looking at the particle motion and saying, well, straight line paths. Well, in reality, even though it may look straight in that demonstration, all of these paths the particles curve towards each other. And again, that's because one particle has a positive charge in the nucleus, the other particle has negative electrons, and they do curve towards each other. Real gases exist. And if we were to consider all of the other factors, our mathematics would get a lot more complicated. So in an ideal gas, do understand what we've done is we've simplified the model. We're going to eliminate some things that make the calculations complex, and we're going to stick with linear algebra. So we're going to neglect that the particles have different sizes from each other, and we're going to neglect the fact that the particles do attract each other to some extent, and we're going to pretend that the particles are always moving in a straight line path. Now, when can we not use these calculations, these equations rather, that we're going to learn in chapter 18 and 19? We can't use them when we get what's called deviations. And deviations are when you predict something, but your results are not near what you predicted. And deviations occur when you can no longer maintain straight line path. And that happens under 2 conditions. One, where the particles are so close together. In other words, they are so concentrated or they are under so much pressure that the paths between them are very small, and therefore they exert a lot of attraction between the particles, causing the pathways to curve. We're going to focus on only 2 factors. The factor where we have to consider how big the particles are, that's going to be a factor of when we're dealing with high pressures. So not normal atmospheric pressure, but maybe something inside of a pressure chamber or a furnace or something else that has been pressurized. We would get deviations. The second is when the particles don't have enough work energy to be able to maintain straight line paths and they start to curve towards each other. That occurs when you have low temperature. Remember, their kinetic energy comes from the thermal environment. So as they lose thermal heat, they lose velocity, and now they can't do the work necessary to maintain straight line paths, and they start to curve towards each other. So we have 2 conditions under which we get deviations, high pressure and low temperature. Now the exact pressure and the exact temperature depends upon which gases you're dealing with and how concentrated they are. All right, so that second part of the essay, first part is what are the properties, compare real gases to ideal gases, and then the next part would be under what 2 conditions do we get deviations. In other words, on what 2 conditions can we not use the equations we're going to learn in chapter 18 and 19, and those 2 conditions are high pressure and low temperature, and you have to explain it. So you can go through the explanation of the book. Again, the explanation in the book is that the volumes of the gases become significant, but the physics is that if you reduce the distance between them, according to Coulomb's law, right, we have force of attraction is equal to some sort of proportionality constant, and then we have the charges Q1, Q2 over d squared. That's one version, the second derivative of Coulomb's law. And so we are reducing this distance between particles, so the force of attraction is going up, and that's an inverse relationship between force and distance between charges. So as the distance gets small, then the force of attraction goes up, and now the particles start to exert a lot of force on each other and they curve towards each other. Your book talks about that under those conditions the particles come together and liquefy. Now, anytime you're in a condition where the particles start to attract each other and curve, the thing that keeps them in a straight line path is work energy. So again, the thermal environment provides that work energy. So you can increase the pressure, but in order to avoid deviations, you would also have to increase the temperature. You have to keep the particles moving fast enough to maintain their straight line path. Okay. So that's chapter 19. I don't know why they wait till chapter 19. I really think it should be a chapter 18 topic, but chapter 18 starts out with these relationships among when you have either a gas by itself in a container or a mixture of gases that are not chemically reacting. And they say that, there are really five things that we have to take, or four things rather, that we have to take a look at that affects the results of how these things behave. And that is the volume of the container itself, the temperature under which we're running the experiment, how much pressure we're dealing with, and the concentration of the particles. In other words, how many particles we have in the container. All right, so the first relationship we actually talked about in chapter 15. Pressure and volume are inversely related. So all that stuff from chapter 15 comes back again. First quadrant graph, we have an inverse relationship, so we have a negative slope, and we're going to put pressure on the y-axis and volume on the x-axis. And when we do initial and final state equations, we get P1V1 equals P2V2. Now notice there's no change in temperature here. So let's say we're running an experiment. Maybe we're running it without the addition of heat, and we're just running it at room temperature. We're not changing the temperature because we're not getting a chemical reaction. We could measure the effects of what's called Boyle's law. And some of the multiple choice questions they like to ask you, and you have to be careful with this because it doesn't apply to temperature. But this is a algebraically inverse relationship. So if you go from a container of 1 liter to half a liter, then you're doubling the pressure from 1 atmosphere to 2 atmospheres. If you go from a container to a container 1/4 the size, from 1 liter to 0.25 liters, like in the third diagram, now you're quadrupling the pressure from 1 atmosphere to 4 atmospheres. Now, Charles' law is a little different. They like to try to trick you on Charles' law. Charles' law was the whole V1 over T1 equals V2 over T2 thing. And with Charles's law, you have to understand that it's based upon Kelvin temperature. Yes, there is a direct relationship there. And what they'd like to do is they like to trick you. They'll say, well, predict the temperature. If you double the volume, what's going to happen to the temperature? So you're automatically, well, okay, direct linear relationship. If I double the volume, I got to double the temperature. So if they give you 25 degrees C, you're like, easy, 50 degrees C. And the answer is wrong. Okay, it's based upon Kelvin temperature. So if you're doubling the volume, you're doubling the Kelvin temperature, which for Kelvin temperature, 0 degrees C is 273 Kelvin. So be careful. All of these things are designed to be done in kelvins. If you start trying to do this in Celsius and Fahrenheit, you're going to run into problems. And again, classical multiple choice questions, they love to try to trick you by seducing you into picking that the relationship is Celsius. It's not. It's Kelvin. We said the other two relationships from chapter 15 was that pressure and temperature. Gay-Lussac's law is also a direct relationship. So P1 over T1 is P2 over T2. And the Avogadro law had to do with the number of particles. That N represents the moles of particles. So P1 over M1 equals P2 over N2. Again, a direct linear relationship. And if you put all of those relationships together, you can get two different things. One, if you're not changing the number of particles, then you get what's called the combined gas law, which is up there at the top. P1V1 over T1 equals P2V2 over T2. Or you get what's called the universal gas law, which is this PV equals nRT. Remember that V stands for the volume of the container and N stands for the moles of gas. Now, R is a constant that makes the relationship mathematically work out. There are several values for the ideal gas constant. It depends upon what pressure unit you use. So if you use kilopascal as your pressure, you should be using liters and moles and Kelvin anyway. But if you use kilopascal as your pressure unit, then you're going to use the value 8.314 for R. Now, you don't have to memorize these values. They'll be given to you on the test. The one that's most commonly used, though, is this one, 0.0821, and that is when you're using atmospheres as pressure. Now, they love to report things in atmospheres in the college textbooks. However, if you're using a pressure gauge, you're going to be measuring pressure most likely in millimeters of mercury. So even though your book doesn't mention it, if you're using millimeters of mercury, 62.4 would be the volume. So 62.4 liters times millimeters of mercury over mole Kelvin. And we will talk more about the gas law constant in chapter 19. Okay, these initial and final state problems. So if they give you a problem like this, you have to decide, well, which relationship am I going to use? Boyle's law, Charles' law, Gay-Lussac's law, or Avogadro's law? And I had really two answers to that. One, you don't have to use any of them. You could use PV equals nRT. That's how I'm going to do it. For instance, that would be the AP style of doing it, but you're not required to do the AP style. Let's say we take PV equals nRT, and we write P1 V1 equals N1 R1 over T1. And we're going to put that over P2 V2 equals N2 R2 T2. Okay. Now, if I have a problem where the temperature remains constant, then in this relationship, I can cancel temperature out. Well, gas law constant is a constant, so we can cancel that out also. But suppose I'm keeping the volume of the container constant. It's a metal container. It's not going to expand or contract, so it remains constant. So that leaves us with P1 over P2 equals N1 over N2. Now, if I cross multiply, I get P1 N2 equals N1 P2. And then if I divide by N1, then I get P1 over N1 equals, if I rearrange this rather, then I get P2 over N2, which is Gay-Lussac's law. So all of these relationships, Gay-Lussac's and Boyle's and Charles's law, these are all derived from the universal gas law, PV equals nRT. So you could just use that rather than having to worry about remembering any of the other relationships. However, here's the reality of things. When you're taking a test, whether it's honors or AP level, and you have to take multiple choice, you're on a time limit. If you know the relationship to use, it's a lot easier just to use that relationship than to go through the derivation that I just showed you. So even though using PV equals nRT for chapter 18 is what they call good pedagogy, it's a good way of learning. It reduces the amount of memorization and recognition that you have to do. I would say that being familiar with the other relationships will actually save you time on the multiple choice test. So let's go back to our little problem here. Pressure of a used spray paint can is 218.5 kilopascal, and they give you the volume of the can. Truck's going to run over it, and it's going to reduce its volume to 41.3 milliliters I got this from textbook worksheets, by the way, in such a magical way that the truck runs over the can without bursting the can open. So all the gas stays trapped inside the can. All right, so what's the resulting pressure? Glad you asked. We could just use PV equals nRT and then cancel out the things that aren't changing. The second way that you can determine the relationship, though, and I mentioned I was going to tell you earlier, is to take a look at what's changing and what's not changing. If things aren't changing, then they're going to cancel out in an initial and final state problem. We just saw that with PV equals nRT, that the temperature wasn't changing, so it canceled out, and the volume wasn't changing, so it canceled out. It didn't wind up in our equation. Gas law constant was constant. Didn't wind up in our equation. We only put things in our equation that are changing. So when I look at this problem, I say, well, should pressure be in my equation? Well, absolutely pressure should be in my equation because they're asking me what's the resulting pressure. Now, sometimes it'll be an easy question like this where all the numbers are relevant. Sometimes I like to throw in some misleading information. But here, we can see we're starting with 250 milliliters and we're ending with 41.3 milliliters, so obviously volume is changing. Do they mention temperature changing? No. Do they mention the amount of gas changing? Is the gas escaping? Are they pumping more gas in? And the answer is no. So one of the questions students like to ask is, Mr. Burnett, when do you use Boyle's law? I would use Boyle's law when only pressure and volume are changing, and that's the case here. We have pressure and volume only. So I'm going to do P1V1 equals P2V2. And that's a formula, so we got to solve for the variable first. They're asking us for the resulting pressure, so that's P2. So we get P1V1 over V2. And now we can substitute in our values. Now, is our answer going to make sense? Well, if the can gets squished, we would expect the pressure to go up. So we get 218.5 times 250 divided by 41.3. And that's 1,322.6 blah, 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 blah. And I'm looking at a total of 3 sig figs. So 1,320 kilopascal. Do I convert it to atmospheres? To millimeters of mercury? No, because the problem didn't ask me to. Only asked me what was the resulting pressure. Okay, next problem. Again, they give us a volume for a can, and we're compressing it, and they give us a temperature in Kelvin. That was nice of them instead of Celsius. They won't be that nice to you on the test. And what is the new temperature of the gas? So which equation do we use? Well, we're definitely going to use volume, right? Because the volume is changing. Let's copy this and let's paste it. Sorry, I'm still having problems with allergies, so forgive me for breathing heavy and all the coughing and stuff. It's irritating. I listened to one of my videos and I was like, oh my god, that's awful. All right, anyway, so what's changing here? Well, I'm looking at the problem again. They're not giving me any erroneous information. It's always funny about textbooks. When they give problems to teachers to demonstrate, they tend to be easier problems. I guess they don't trust us. But I definitely have volume changing, so I'm going to put volume in my equation. And they're asking me for a new temperature, so I got to have temperature in my equation. And they're not changing anything else. So this is going to be a volume temperature problem, which is V1T1 over V2T2. And they love to have you solve for T2 because algebraically that's a little more difficult. So cross multiply and then divide by V1. Oopsie poopsie. All right, so now we can substitute in T2. And again, it has to be Kelvin temperature. We were lucky because they gave us Kelvin and not Celsius. I can almost guarantee on the test they're going to give you Celsius. And then remember, you got to add 273 to make it Kelvin. All right. Now, why didn't I convert milliliters to liters? Well, both units are in milliliters, so as long as the units are constant, we're fine. The only time that we have to worry about units, two things. One, all temperature is in Kelvin for chapter 18 and 19. And if you're using PV equals nRT, then your volume really should be in liters. All right, so this comes out to be 43.8912, so that's 3 sig figs, 43.9. Okay. What else we got? Hoping we're getting to the end of the video. All right, I'm going to stop the video here, and we'll pick up this STP using the combined gas law in the next video. Thank you very much.